Okay, thanks so much for coming to the Rutgers Experimental Math Seminar. Today's speaker is Rodrigo. Perez, right?
Perez.
Yeah, okay, Perez, who will talk about fascinating things involving the Catalan numbers. As usual, please mute yourself unless you have a question. Thank you.
Right. So let's first make sure that I can share everything here. Can you see it?
Yes.
Okay,
Yes.
perfect. So the usual comments in the beginning. Thank you very much for the invitation. I'm very happy to finally share this work with people in combinatorics. The motivation is from dynamical systems, complex dynamics, and there seems to be a big gap of communication between the two groups. So I'm very happy to be able to present these ideas. Second thing to mention is this is joint work with Magnus Aspenberg from Lund University in Sweden. And this is a project that's been going on for almost 20 years. We have not finished proving one part of the big result that we're chasing, but there's a lot of nice mathematics that has shown up in the intervening years. So first, some motivation from complex analysis. We know the Riemann map. It tells us that you have any simply connected region other than the full plane, there is a holomorphic map that sends that region to the unit disk with certain extra conditions. And when we learn complex analysis, then we learned all of these horrible functions that take a square or a triangle or some basic regions that for which we can construct a nice map to show the corresponding Riemann map. But the big deal about this theorem is that it's talking about any simply connected region, no matter how horrible the boundary is. So here I have an example here of a simply connected region, this white region inside. Can you see the mouse, by the way?
Okay. Yes.
So this simply connected region, but the boundary is not locally connected. You have an infinite accumulation of segments here, and it's going to be a horrible boundary. Still, there will be a Riemann map, a holomorphic map that takes that simply connected region to the unit disk, with a choice of point going to the center and a choice of derivative. But basically, that's the main idea. And then the thing is, if we can take an arbitrary point into the disk, we could think about taking that point, moving it to the disk, and then just start to rotate it. Round circles in the unit disk become level curves in our original region, and we have a rotation in our region, a rotation that will have nothing whatsoever to do with the boundary itself. But the boundary is not part of the region, so we don't care about that much. So here's the idea. We have a function from our region to itself, given by the composition of the Riemann map to the disk, a rotation, and the inverse of the Riemann map. Or actually, this is what we call the Riemann map. This would be the inverse of the Riemann map, the general consensus. Here, I'm multiplying by lambda, a complex number of unit size, and that's going to be the rotation. And that lambda is what we're going to be chasing. So the question is, if I have different regions, I have different maps, is it possible for that function to be polynomial for certain regions? And the answer is not completely transparent. And once that we have something that is nice region, a nice function, what is going to be the geometry of the corresponding region? What happens with its rotations and so on? So the main example is this one. I have a quadratic polynomial, so nice function, very specific constant here. The set in black is the Julia set of the function. I will not define it, but part of the complement of the Julia set is this gray region, which under the quadratic map maps to itself. And because it maps to itself and is simply connected, what we have here is essentially the composition of maps that I mentioned before. And we can talk about a rotation in this simply connected domain. For this very simple example, the critical point of the function f is 0. The derivative here is 2c, so the critical point is 0 and is in the center of the picture. And the image of the critical point is the critical value, which is located somewhere around here in the boundary. Both the critical point and the critical value in this particular case are located on the Siegel disk, which is this region. And the rotation number, in this case, these parameters are chosen so that the rotation number is the golden ratio, meaning that after one application of function f, things rotate by about 60% of a full turn around the disk, right? So angle 2 pi phi. When we have a nice function that has such a domain mapping 1 to 1 onto itself, that automatically gives the Riemann map, and that's what we call a Siegel disk. The paper that Ron was mentioning is one that I published in the notices of the AMS, giving a historical account of the paper of 1942 of Siegel, where he proved that such regions exist.
This number 0.39054 plus 0.5867, is it, etc., is it a root of some polynomial?
Yes, so this parameter is on the boundary of the main cardioid of the Mandelbrot set, and when you have a parameter in the boundary of the main cardioid, what that implies is that the critical that the derivative at the fixed point is unit size, and that's what we want, so that the conjugation is a rotation; it doesn't shrink or expand.
But this number, is that random, or it came up from something, the parameter?
Yeah, it's related to phi by some.
Okay.
There's a square root or 2 in the transformation.
So the typo, so it goes forever, right? It's not a...
Yeah, oh yes.
Okay.
Yes, that's an approximation.
It's that,
yes.
that, okay.
Yep. Okay, so there is a conjecture of Leonard Carlson about, I don't know, almost 40 years, about this very specific Siegel disk, not any polynomial, but a quadratic polynomial, and not any rotation number, but the golden rotation number is one specific example. And the conjecture is the following. The center of rotation of the Siegel disk is right here at the tip of the cursor, and the critical value is here in the boundary. The distance between those 2 points are easy to compute, and the distance is 1/4. And the conjecture is that this 1/4 is the distance from the center of rotation to the boundary, that there is no other point on the boundary closer to the center of rotation than the critical value. This is a tremendously difficult conjecture to work with, because the geometry can be very complicated. The critical value could be hiding behind a spiral of the boundary here, or behind hairs of the boundary. If the boundary is not locally connected, it's a very complicated geometry that may hide the critical value from being the closest to the center. But if the distance to the center of rotation is 1/4, then it is attained by the critical value, and that is a conjecture.
Do you have lower bound and upper bound for the distance?
Well, the upper bound is 1/4 because of the critical value. The point is that this computer picture that looks very crisp and clear could be completely misleading. There could be tiny hairs of the boundary that are coming very close to the center of rotation that one cannot detect in the computer, and there's no easy way to falsify that possibility.
Thank you.
Okay. So our strategy to attack this conjecture is simply to take the Riemann map from the Siegel disk to the round disk, compute the power series, and try to get the exact radius of convergence. If the exact radius of convergence is 1/4, then we can guarantee that there is a disk of radius 1/4 inside, and that proves the conjecture. That would prove actually more. because if you have a disk of radius 1/4, that means that you can fit a small angle, a tiny angle very close to 180 degrees at the critical value. And that would mean that the angle at the critical point is at least 90 degrees, that you can fit an angular wedge of 90 degrees at the critical point. The computer picture seems to suggest that the best angle would be 120 degrees. So it sounds like this would be an easy conjecture to prove, but it's actually very difficult. But in brief, our strategy is simply to write the power series of the conjugating map and straight away not search for a bound, but get the exact radius of convergence. That's the conjugation, that's the Riemann map, go to the disk, rotate, that's the same as applying the function, the quadratic function, and then conjugating to the disk. And with this conjugating map, conjugating equation, we get a recursive formula for the coefficients of the map phi. And this formula has two parts. There is a factor depending on lambda, on the rotation number here, and another fact that looks combinatorial. It's a recursive formula. Here are the previous coefficients. The great difficulty of these problems arises in the fact that this formula has this quotient where we're dividing by 1 minus lambda to the n. Remember, lambda is a rotation. It has to be an irrational rotation, but that means that for high powers of n, occasionally lambda to the n is very close to 1. So you have a very small denominator, so this coefficient can be extremely large. So depending on lambda, sometimes these coefficients are very large, very often for many n's, and that means that the coefficients of the conjugating map will grow super exponentially and there is no radius of convergence.
But formally, it's not a rational function. Each of a sub n is not a rational function of lambda, and you can compute.
Yes. Yes. Well, that's what we're trying to do. So it's a recursion for the coefficients, and then each of the coefficients depends on lambda in this complicated manner.
Okay.
So the paper of Siegel was proving that the growth of these coefficients is exponential when lambda, the rotation number, is Diophantine. And therefore, there's always a positive radius of convergence. Therefore, there is a Siegel disk when the rotation number is Diophantine. Okay. So here's the recursion. And I owe you about an hour of mathematics that I'm going to skip in order to show you, to claim that you can break the recursion and write a formula for these coefficients directly in terms of lambda without the recursive part. And it's this formula. And I'm not going to justify this one. That's a long process. It's a paper by itself, and that's not what I want to talk about today. But at the end of the day, the point is that the coefficients that we are interested in are given by a product of two terms. One term that depends on lambda, and one term that is purely combinatorial. The term that depends on lambda, when lambda, the rotation number is Diophantine, this term is bounded, and we can completely forget about it. So we just have to look at this other expression. This expression is constructed the following way. Fix your n, say 9, build this pyramid, and then fill the pyramid as much as you want. For example, I fill it with 1, 1, and 3, 2, 3, etc. You can see what's going on. And keep track of every position where there is a descent from 3 to 2, from 3 to 1, from 5 to 4. This particular way of filling the pyramid has this descent sum 3 plus 3 plus 5 equal to 11. So this particular filling of the pyramid would contribute lambda to the power 11 to this sum. And then we add over all possible fillings of the pyramid. So 9 is too large, so let's do the example of n equal to 4. there's a pyramid and all the possible ways of filling the pyramid. There are 24. And once that you compute all the possible descents for each one of these ones, this is the total contribution that you get. For example, this path has a descent at position 3, so that contributes lambda cubed. This has a descent at position 2. So
the 14 is the Catalan number.
Exactly, that's where it's coming. So there's a descent on position 2, so this path contributes lambda square. And then there's some other paths that do not have a descent, and they contribute lambda to the 0 or 1. Right? And exactly what Doran was mentioning, this 14 in the total sum comes from the fact that there are 14 paths that do not have a descent. So remember, since the other term is bounded, our goal is to show that this sum grows exponentially with the order of 4 to the n, perhaps with a polynomial term or something, but exponentially the exponential rate of growth is 4 to the n. And because we have Catalan paths, our strategy would be to collect all of the paths in this collection into equivalence classes, where each equivalence class contains one of the Catalan paths, and then focus on the contribution that each one of these equivalence classes gives to the total sum, and show that each one of those contributions separately is bounded. I will mention that again once that we see how this goes. So the way to do this equivalence class, we have discovered several methods, but this is the one that actually works for this situation, but we have some math about other codification of Catalan families in this setting. So what we're going to do is take one of these paths and treat this as a lemma code. It's not exactly a lemma code, but it's very similar. So remember, so the path that I'm showing here is, I believe, the one I have in this picture, right? And these numbers just tell you how you fill everything. Each of these numbers has to be at most equal to the position that is in. So this is column 9, and the number in column 9 cannot be bigger than 9. This is in column 4, and the number appearing here cannot be bigger than 4. Well, that path encodes a certain permutation in the following way. Just read your path and place numbers in the correct position. So number 1 is in first position. Well, there it is. It's by itself. The number 2 has to appear in the first position relative to whatever is written so far. So there it is. And number 3 has to appear in the third position relative to whatever is present. So it has to appear on the right side. Number 4 has to appear in the second position. So somewhere here in the middle. There it is. Number 5 has to appear in the third position. So somewhere here. And there it is. Number 6 has to appear in the first position. So it has to land to the left of 2. There it is. 7 in the fifth position. 8 in the fourth position. And 9 in the seventh position, which is here. And that describes a permutation. And this process is bijective. So from the permutation, you can recover the original worth. We had descents in the original worth, and each descent translates into an instance of the pattern 213, where the left and right values are consecutive. And because they're correlated, instead of calling the descents, I'm going to call those instances descents. So there's a descent at position 3 in the path, and that corresponds in the permutation to the number 3 appearing to the right of number 4, jumping over a smaller number, in this case 1. The descent at the position 5 corresponds to 5 being to the right of 6, jumping over a smaller number 2. And the descent at position 7 corresponds to 7 being to the right of 8, jumping over the smaller number 5. So that's what I call a descent in a partition. If I have a path without a descent, that translates, of course, to a permutation with no descent. And I will show you a bit about how those are formed. The two examples that I showed you in the previous slide were chosen because they have the same tree structure, the same binary tree structure. The root of the tree is going to be the bottom number, in this case 1, and there is one number to the right on the right sub-branch. For these two permutations, the numbers are different, but to the left, there's going to be one smallest number, which in this case is 2, corresponding to this vertex. And starting at this vertex, there is a sub-tree with one branch to the left, so one number to the left, and one branch to the right, where this next bigger number is, that's the 4, the next number, that's the 5, and to the left of 5, there is one number, and to the right of 5, there's 2. So 8 or 6, 7, 9, or 7, 8 in these two different cases. So these two permutations have the same binary tree structure, and this is going to describe our equivalence class. So pick a binary tree and collect all the permutations that have that binary tree structure. For all of those permutations, we collect the descent contributions, and we get a polynomial associated to that tree. So I mentioned that there is always one permutation that has no descents, and that's the permutation that we will obtain if we label the tree starting from the root 1, 2, 3, 4, 5, 6, 7, 8, 9, going around the tree in clockwise fashion. And that's this permutation down here. That permutation contributes a 1 to the sum of coefficients for this tree. All other permutations contribute some power of lambda, and I will give you an example. So our revised goal is the following. Given one binary tree, we want to collect the contributions, the lambda contributions of all permutations that have that binary tree structure, and then prove that for that particular binary tree, the sum of contributions is bounded. And again, since there are Catalan many such trees, we will have the number of equivalence classes is of the order of 4 to the n. If each one of those equivalence classes is bounded, then the total sum of contributions will have exponential growth 4 to the n. The radius of convergence is 1/4, and we prove the theorem. So just to give you an example of how this works, here's a specific tree, a simple one, and these are all the permutations that have this tree structure. 1 goes in the root, and there's one number to the right, could be 2, or 3, or 4, or 5, and for each situation, there's 2 different ways of filling the rest of the tree. The descents for all of those 4 permutations are given as follows, and that means that the total contribution of this tree is this polynomial. Now, this is not a very particularly nice polynomial. It's kind of ugly. It doesn't factor nicely, has no interesting properties, but there's something very nice. Imagine that instead of the permutations of 1, 2, 3, and 4, we use permutations of 0, 1, 2, and 3. So the descents that we'll have obtained will be reduced by 1. Instead of the correct descents that we have obtained, everything will be reduced by 1. And if you collect all the powers of lambda corresponding to this, you get this polynomial, which is actually very nice. It factors nicely. And this factorization is very enticing because this factor is exactly the contribution of this left subtree. I don't know if I'm blocking it. Can you see it? This is the exact contribution of this tree.
I see.
And the other polynomial, the cubic polynomial, is just a Gaussian binomial, and it describes the allocation of 3 vertices on the left and 1 vertex on the right. Because I'm using the parameter lambda, I didn't want to call these q-binomials. I will call them Gaussian binomials, which is not exactly the correct way to measure Gaussian polynomials or q-binomials, but that's a difference in notation. Okay, so the result in this direction, the first result in this direction, is that if we have a tree, a binary tree, which splits into two subtrees, the left and right subtrees, the reduced contribution of the tree is going to be the product of three things: the correct contribution of the left tree, the correct contribution of the right subtree, and the reduced contribution of a tree that is unbranched with m vertices on the left and n vertices on the right, just a letter V. And that reduced contribution is exactly a Gaussian binomial. So in order to prove a result like this, we had to deal with the fact that sometimes the polynomial is reduced, sometimes the polynomial is not reduced, and we had to have the following observation.
But you use lambda instead of q, I guess, for the Gaussian.
Yes, exactly. That's why I don't want to call them q binomials, because I'm using lambda.
So lambda binomials.
Exactly. So if I have a permutation that has descent 2, that will contribute lambda squared to the correct polynomial, but only lambda to the reduced polynomial. But if the permutation has two different descents, the correct contribution would be 6, lambda to the 6th power. But if I reduce those, I will have to reduce the exponent by 2 for that polynomial. So I cannot just reduce everything by 1 everywhere. It depends on the number of descents that I have present. So I have to use a two-variable polynomial to keep track of how many descents I have in each of the permutations. So for this example that we have been looking at, these are the descents. If there is no descent, that's one possible permutation in the tree, the contribution is 1. If there is exactly one descent, these are the possible contributions. And there are two trees that have two descents, and their contributions are encoded in this portion associated to the factor of mu squared. So mu counts the number of descents in one particular permutation. Now, classically, the Gaussian binomials enumerate paths in an n by n grid, and they split them according to the area statistic. So we will have the same distribution, binomial distribution, but for a different statistic. If you tilt your head 45 degrees, this looks like a tree with two vertices on the left and two vertices on the right, but no branching. And on that tree, there's different permutations, but each of these paths describes one of these permutations where the order in which you follow the down segments and the right segments corresponds to putting a number in the tree, to filling in the tree with numbers. Every down corresponds to putting a number on the right. Every right stroke corresponds to putting a number on the left. So if I go down and then, a right and then a down, that corresponds to a number on the right branch jumping to the left branch. So these corners count the descents in such an unbranched tree. These are all the possible paths in this situation. And if we count the position of these corners, then I get exactly the same distribution. This path has a corner at position 1. This should be lambda. So position 1 corresponds to lambda to the first power. This path has a corner at position 2. This path has a corner at position 2, so those correspond to two contributions of lambda squared. I have one path where the corner appears at position 3. That corresponds to this contribution. And at the end, I have one path that has two different corners at position 1 and 3. So the total contribution is lambda squared, but that goes with the coefficient mu squared because there's two contributions. But other than that, is the exact same binomial distribution. Right. So if you just make mu equal to 1, you get the binomial coefficient. And if you substitute mu equal to lambda, well, that mu equal to lambda lifts this exponent by 1, lifts this exponent by 1, and lifts this exponent by 2. So that is basically on reducing this polynomial to get the correct contribution, the horrible polynomial that corresponds to that unbranched tree. So for unbranched trees, that polynomial gives me exactly what I wanted. But most trees are not unbranched, and that's why we have to get that theorem I mentioned. Okay. So how does this work? Why is it that the binomial coefficient enumerates those paths if they're ranked by the sum of corners? Well, the reason is that if we restrict to paths with exactly C corners, the horizontal coordinate of each corner adds up to this value distributed by a binomial coefficient. The sum of vertical coordinates for all the corresponding coordinates is a similar expression. It's a little bit different, and I'm going to go into details about how to compute that because it's just technical computation. So that the total sum of contributions with exactly C corners is the product of those two binomials and the product of these two powers of lambda, which is just lambda to the C squared. And that sum is exactly Vandermonde decomposition of the binomial m plus n plus n.
The Q Vandermonde identity.
Yes, but this is not the standard way that is always written. This is a little bit more symmetric, which works in our advantage in the next step. So this explains why this binomial is exactly what enumerates all those paths. And it's a simple result, different statistic, the sum of corners, but it has the same distribution as areas under the paths. But when we are talking about the trees in the left and right subtrees in a more complicated tree, those may actually hold descents that jump across from the right to the left branch. So the left subtree, for example, will have n vertices on its own left, n vertices on its own right sub-branch. And then the binomial would describe the number of descents except for two reasons. One reason is that the vertex levels are going to be shifted because the subtree is hanging from the root. So it never gets the number one, so you have to increase the numbers that label the tree. This is the source for all of this business about reducing and unreducing the exponents and why we have to do all of this. But the second reason is that this left tree may receive extra descents that come all the way across from the right subtree. A number on the right subtree that goes across the root to the next value on the left subtree. And we have to count those descents as well. So those extra contributions increase the amount of contribution that each permutation provides. And we figured out that the pattern of increase is given by a grid by an ornamentation on the grid. So depending on what happens, what numbers go in the left and what numbers go in the right, you will have different ornamentations. And then there's a whole business about how to add all of those things together to get the theorem dimension. But once that you restrict your grid to one specific ornament means selecting some vertical coordinates and selecting some horizontal coordinates. In this particular case, I selected one vertical coordinate, I selected one horizontal coordinate. And with that choice on each path, we have extra, let's call them honorary corners. It's not a real corner, but it's indicated by the arrow, so I call that a corner. This other arrow gives me an extra corner in this path, not a true corner, just an honorary corner. I painted in green. This path has a genuine corner here, and then honorary corners because of this arrow and because of that arrow. The genuine corner here is just a genuine corner, so there's no new honorary corner added because of this vertical arrow, but the horizontal arrow does add a new horizontal honorary corner, and so on. In this case, there is nothing new added because the authentic corner happens to intersect both the vertical and horizontal ornaments. If you make the count of descents, in this case, you get a completely new count. For example, this path has a descent at 1, a descent at 2, and a descent at 4. Those two are honorary, but we're counting them. So this path contributes 3 descents. So it's going to contribute a power of lambda to the 7th. And so on. With the ornamentation, the corresponding polynomial is the following. There is one path with one corner, and it contributes 3. Lambda to the 3. That's this path. There's 4 paths with 2 corners. 1, 2, 3, and 4. And they have these contributions respectively. 2 of them contribute 5, which would be, let me see, this one with 2 plus 3, and this one with 1 and 4. And there's going to be one path that has exactly 3 corners, and that's the one I mentioned here, and the sum of contributions is 7, so it contributes the lambda to the 7. So this is the 2-parameter polynomial, the 2-variable polynomial. But if you substitute mu equal to 1, you get this contribution, which is just a shifted multiple of the same Gaussian binomials. So the big theorem is that no matter what ornaments you get, you will get a shifted version of the very same Gaussian polynomial that describes this grid. And more concretely, if you have any given ornamentation, then the contribution that you compute is the Gaussian binomial associated to that is going to be just a Gaussian with some extra power of lambda, and that's going to be given by some power of lambda that we have here that we'll mention in a moment, times a Vandermonde convolution of binomials with lambda corrections, where the sum is done over a fixed number of corners for all the paths, and each one of those terms corresponds to a mu to the c, and that's how we collect these terms by the number of corners.
This is a 2-variable extension of the Gaussian polynomials with 2 variables, lambda and mu.
Well, so basically the result is that the contribution is always going to be a Gaussian polynomial with an extra factor of lambda. But the way that we know that that's true is because that is given as a Vandermonde decomposition, which is split in 2 variables.
So this is the generalization. When you specialize mu to be 1, you get the usual q Vandermonde.
Exactly. Exactly. But this is, so you could think of this as a two-variable generalization of the Vandermonde.
Oh, that's nice.
And I probably missing something. What is S? You have lambda
Yes.
to the S. What is S?
Yes, I was going to mention that in a moment. So lambda S is the correction term that we need, which is going to be the total sum of vertical coordinates that are marked and the sum of all horizontal coordinates that are marked. So in this particular example, for this particular ornamentation, starting at 0, the vertical coordinate is at position 2. And starting at 0, the horizontal coordinate is at position 1. So this ornamentation has S equal to 2 plus 1 equal to 3.
Okay.
And here is the lambda cubed. Okay, so we know exactly what to obtain. And now the proof of this result is a technical thing, and I wanted to give a motivation for the entire problem, so that I knew I would not have time to prepare even a hint of a proof of this main result. But
it's in the paper, right? So you can give references to your paper.
Yes, I didn't put them here, unfortunately, but it's I think I will have to find those references while we're talking after I'm done to give you the exact reference, but I'll find it in a moment.
Okay.
Of course, it's in the archive, but it's already published. So it's basically the main result from the combinatorial point of view is that each different grid ornamentation has its own two-variable Vandermonde decomposition. And that's the result. Thank you.
Thank you for a fascinating connection of very deep dynamical system to combinatorics, also complicated. So let's thank Rodrigo, and we have time for questions. So it's really fascinating, the connection between. So you find some new combinatorial identities. So famously, the Gaussian polynomials are given by bounded partitions. So can you relate your two-variable thing to zero partitions, or you need these particular pyramids?
I'm not sure what you mean by bounded partitions.
Well, famously, the Gaussian polynomials m plus n choose m is the generating function of integer partitions.
Oh, okay.
With its most largest part m and its most n part, and this is the usual interpretation of.
Right. Yeah. Okay. Yes. So this is a combinatorial result that comes out of our working on the dynamical conjecture. So we have not explored all the combinatorial possibilities of that. But if there's a way to make a connection, that would have to require finding an interpretation of these ornamentations in terms of partitions.
Yeah, it'd be interesting.
Yep.
And so do you succeed in proving that it's bounded by 4 to the power n?
Well, remember I told you that there was an initial part where, which I was not going to mention because it's a really long derivation.
Yeah.
Here, how to go from the recursion to this formula.
Yeah, that's beautiful combinatorial interpretation of this object.
We have, I have another hour and a half talk to explain how to get from the formula for this one over here, to it's a recursive formula, right? So how to get from this formula to something that that can be applied to a particular tree. So how to break the recursion to get a description of all the binomial coefficients that appear in the description of the actual tree. Bear in mind that this result is for the reduced polynomial of the tree, and we really need the unreduced version of the polynomial. Otherwise, the coefficients point in different directions, is complex numbers, and we don't get the correct values. So starting with this decomposition, we had to know how to unreduce this polynomial. We can do that because we have a version in two variables with a mu, and then we can substitute mu equal to lambda to do the unreduction. And we still had to figure out how to apply the Diophantine properties of lambda to evaluation of the sequence of binomials that we obtain.
No, that's very interesting. The combinatorics is beautiful and the connection, but the initial motivation was to prove that something is bounded by 4 to the power n, right? Something like this, if I remember.
Yeah, exactly. So we're at the stage where we now have a complete expression for the polynomial, and we have some results about what happens when you evaluate those binomials at values of lambda that have Diophantine rotation number.
But did you succeed completely or not yet?
Not completely, not yet.
Okay, good luck.
Yes,
it's a beautiful approach. Other questions too, Rodrigo?
You use the phrase ornaments on the grid, and I'm not sure I understand the rules for how those are chosen or determined.
So the basic grid looks like this, and then you could count the paths according to area, and that's the standard binomial coefficient. You could count the paths according to corners, right? This is corner position 1 and 3, so that's 1 plus 3 is 4, so that's what this one counts. But if I add an ornamentation to the grid, then I'm going to count corners differently. So what an ornament is selecting a few vertical coordinates and selecting a few horizontal coordinates. Not all of them, maybe none of them. In this case, I selected one vertical and one horizontal for illustration purposes. Those are the ornaments, and what the ornaments do is think of them as lasers. So I point a laser down, and when it shines on the path, that automatically becomes a corner in my count.
So how many different ornaments could you choose in this case?
You could choose anything. So you can have a laser, let's call them lasers. You can have a laser in the first corner because that's where you're starting, and you can have a horizontal laser in the bottom position because that's where you finish. Any other vertical coordinate or horizontal coordinate could be on or off.
Okay, I see. Thank you.
Yep. And for each one of those, you have the corresponding binomial, Vandermonde convolution. Many of them are actually the same Vandermonde convolution, just with different extra factors of lambda. And now, while we were talking, I found the paper. It's in Discrete Mathematics. It's December 2022. That's volume 345. I'll put it in the chat.
Oh, thank you. So Rodrigo, it'd be nice if you email me the slides with your permission, so I can
absolutely
them, along with the recording, be available next week. So maybe in the slides you can also add references to your paper with Aspenberg. That'd be useful. Yeah. So I was still. So you finished all the combinatorial part, right? But basically, you're still working in using it to prove the bound, right? That my
yes.
Right?
Yes. And we already have some nice results about evaluating binomial coefficients at values of lambda that are complex numbers of unit size. So let's say roots of unity, for example. So I have to mention something very important. Remember, the conjecture is for one very specific value of lambda. Let me go back to that picture. Just so that you get a flavor for how difficult this problem is.
Yeah.
We're exclusively talking quadratic polynomials, and that's part of that is what makes this specific conjugating equation give this specific formula over here. But the rotation number that one obtains in this particular case is just the golden number. That's a nice number, but the Diophantine properties are very, very strange. If you pick square root of 3, which is very Diophantine, but the continued fraction is periodic of period 2, then you will have spirals in the boundary for some dynamical reason. And those spirals hide the critical value away from the center of rotation. So the critical value cannot be the closest one. The radius convergence is smaller than 1/4 because of that. Even though square root of 3 is perfectly Diophantine and periodic and nothing too ugly about it.
Yeah, that's very subtle. So for the golden ratio, it's conjecturally 1/4.
1/4. And I think that modulo some basic ways of messing with it, the conjecture is that it will be the one and only rotation number for which the radius convergence is exactly 1/4.
Thank you.
I have a quick question.
Yes.
When you basically generated all the permutations corresponding to a tree, I think it was few slides. Yeah, here, like there is a simple way to do that, right?
Yeah, there's different ways to do it. You can do it from left to right, top to bottom. There's different ways of doing it. This is the one that actually works for us because if you remember, let me see what is the other slide. Yeah, here. If you remember, descent on a permutation is a number jumping to the left to the next number, going across a smaller number, right? So 8, 5, 7. Well, what that means is that I have label 8, 5, and 7 in here. If I use this particular way of labeling the tree, right? So a descent on the tree, according to this method, is exactly separating 7 from 8 by the common root.
Okay.
Right. So there's other ways of filling the tree to make permutations associated to the tree, but this is the one that works for descents.
Yeah, but because without this descent tracking, there is a simple formula to find how many such permutations correspond to a given tree. That's by Donald Knuth, I think. Yeah.
Anyway, I think it's a good time to stop. Thanks so much, Rodrigo, for a very fascinating talk. And please email me the slides when you have a chance. Thanks so much. There's no talks next week because we're doing New Year's, but in 2 weeks, Neil Sloan will speak exactly on his birthday. Everybody is welcome to come to Neil Sloan's talk in 2 weeks. Thanks so much. And
thank you very much.